Approach procedure design is a particular skill that must enable an approach to be flown in safe airspace. As the procedure takes the aeroplane closer to the runway and the ground, the safety limitations must be increased. Pilot skill, or autopilot accuracy, combined with the inherent errors of the ground-based equipment, must be taken into account when producing approach designs. The 5 segments of an instrument approach are shown here. They are arrival, initial, intermediate, final, missed approach. The vertical cross-section of each segment is divided into primary and secondary areas. Full obstacle clearances are applied over the primary areas, but reduced to zero clearance at the outer edges of the secondary areas. You should recall the discussion of minimum obstruction clearance, MOC, and its application from the previous lesson. Wherever possible, a straight-in approach will be specified which is aligned with the runway centerline. In the case of a non-precision approach, a straight-in approach is considered acceptable if the angle between the runway and final approach track is 30 degrees or less. If terrain restrictions preclude a straight-in approach, a circling approach will be specified. Minimum sector altitudes, MSA, are established at all aerodromes and provide at least 1,000 feet obstacle clearance within 25 nautical miles of the homing facility, NDB, or VOR associated with the approach procedure at that aerodrome. In the UK, MSA is specified for each of the cardinal magnetic compass quadrants. On approach plates, the MSA is diagrammatically represented. The lowest level permitted for an arrival route will be the MSA for the appropriate quadrant that contains the arrival track. All procedures depict tracks, and all pilots must attempt to maintain the required track by flying accurately and applying corrections for known wind. Whilst flying an ILS precision approach, pilots are expected to be able to fly the aeroplane during the final approach phase with a track accuracy equal to no worse than half full-scale deflection of the ILS indicator needle. Aeroplane performance has a direct effect on the airspace and visibility needed to perform the various manoeuvres associated with the conduct of instrument approach procedures. The most significant factor is aeroplane speed. 5 categories of aeroplanes have been established based upon speed at threshold. VAT equals 1.3 times the stall speed in landing configuration at maximum certified landing mass. This provides for a standard basis for relating aircraft manoeuvrability to specified instrument approach procedures. For each approach, an OCA or H is calculated in the development of the approach procedure and published on the instrument approach plate. The vital factor is that the minima can only be deliberately exceeded when the visual criteria continue to be achieved. In the case of precision, non-precision and circling approaches, an OCH or A is specified for each category of aeroplane. The OCA or H is defined as follows. An OCA or H for a precision approach procedure is defined as the lowest altitude, OCA, or height above the elevation of the runway threshold, OCH, at which a missed approach must be initiated to ensure compliance with the appropriate obstacle clearance criteria. This is very similar to the definition of decision altitude or height. The decision altitude or height, DA or H, for a precision approach procedure is the lowest altitude or height above the elevation of the runway threshold, at which a missed approach must be initiated when the required references to complete the landing visually cannot be seen. Going around at this juncture will ensure compliance with the obstacle clearance criteria of OCA or H. The various factors which dictate that the DA or H equals or most often exceeds OCA or H are shown in the diagram. The OCA or H for a non-precision approach procedure is defined as the lowest altitude, OCA, or height, OCH, above the aerodrome elevation of the relevant runway threshold, if the threshold is more than 7 feet below the aerodrome elevation, below which the aeroplane cannot descend without infringing the appropriate obstacle clearance criteria. Again, this is very similar to the definition of minimum descent altitude or height, MDA or H, for a non-precision approach. That is, the lowest altitude or height above the aerodrome elevation or the relevant runway threshold, if the threshold is more than 7 feet below the aerodrome elevation, below which the aeroplane cannot descend without seeing the required visual references. Again, not descending until visual will ensure compliance with OCA or H criteria. The OCA or H for a visual manoeuvring procedure is the lowest altitude, OCA, or height above aerodrome elevation, OCH, below which the aeroplane cannot descend without infringing the appropriate obstacle clearance criteria. The minimum descent altitude or height, MDA or H, for a visual manoeuvring procedure is the lowest altitude or height above aerodrome elevation, below which the aeroplane cannot descend without seeing the required visual references. Hopefully, the pattern has now become obvious. In general, approach minima are developed by adding the effect of a number of operational factors to the OCA or H to produce, in the case of precision approaches, decision altitude or decision height, DA or DH, and in the case of non-precision approaches, minimum descent altitudes or height, MDA or H. The factors that are taken into account when determining this calculation are aircraft mass, elevation or pressure altitude appropriate to the elevation of the runway, temperature, wind, runway gradient, condition of runway. Each system used in precision and non-precision approaches have system minima which are reproduced here. The minimum obstacle clearance is defined for all aeroplanes as a fixed margin which is to be added to the height of the dominant obstacle. For a precision approach, MOC is implicit in remaining no more than half-scale deflection of the needles on the display. For a non-precision approach with a final approach fix FAF, 75 metres, 247 feet of MOC is guaranteed in the primary area. Without an FAF, 90 metres, 295 feet is guaranteed. The MOC is provided for the whole width of the primary area, and in the secondary area, MOC is provided at the inner edges, reducing to 0 at the outer edges. Fixes and points used in designating approach procedures include, but are not limited to, the initial approach fix, IAF, the intermediate fix, IF, the final approach fix, FAF, the holding fix, and, where necessary, the missed approach point fix, MAPT, or the turning point, TP. Fixes are normally all derived from standard navigation systems. Because the standard navigational systems have accuracy limitations, the geographic point which is identified is not precise, but may be anywhere within an area called the fixed tolerance area, which surrounds the plotted point of intersection. The dimensions of this intersection fix area are determined by the accuracy of the systems that provide the information to define the fix. These are defined by ground station tolerance, airborne receiving system tolerance, flight technical tolerance, how accurately you can fly, distance from the facility. There is a difference between the tolerances of the approach procedure intersecting facility and the along track facility. This is accounted for by the fact that flight technical tolerances are not applied to the former. The values illustrated here are used in the development of instrument procedures. Whilst using instrument approach procedures, you will often be using reporting positions and turning points that have been referenced to navigational facilities. For example, when leaving airways, you may be given radar vectors to a point that initiates the start of the arrival route. ILS systems use outer and middle markers that operate on 75 MHz, and some NDB approach procedures utilize these markers. The accuracy of these systems is shown here. Most procedures require you to track overhead a position. This may be at the beginning of a procedure or used to define a point along it. Unfortunately, most of the facilities used to do this are designed to provide accurate track guidance rather than positional fix information. The tolerances shown here are important for you to know. The tolerances we have shown you earlier determine the overall fixed tolerances for any given type of facility, and it is the variations that are used to narrow or widen instrument approach areas as an aeroplane flies to and from a facility. The area is of standard width of 2 nautical miles for a VOR and 2.5 nautical miles for an NDB at the facility. The optimum and maximum distances for locating the FAF relative to the threshold are 5 nautical miles and 10 nautical miles respectively. The descent gradient allows adequate space for descent from the published height crossing facility to the runway threshold. It is achieved by establishing a maximum allowable descent gradient for each segment of the procedure. The optimum descent gradient for the final approach should not exceed 5%, which equates to approximately 300 feet per nautical mile, which is a 3-degree glide path. Precision approaches use this glide path operationally. A maximum glide path descent gradient of 6.5% is permitted, 400 feet per nautical mile, which equates to a 3.7 glide path. But such descent rates may cause some types of aeroplanes to exceed their recommended maximum rate of descent. Pilots must be aware of this before they start any approach.